Question was that we have three systems till now. We talk about system with memory, system which is memoryless, and system which is invertible. Which one is definitely causal? Let's talk about an invertible system. System like yn is equal to xn plus 1. Is it invertible? It is definitely invertible, because whatever you give it as an input, it has one unique output, no problem. And is it causal? No, because at time 0, I depend on the input at time 1 on future. So this is not causal. So this means being invertible has nothing to do with the causality. Now, system with memory. Very famous example of a system with memory is this. Now, is this system causal? It looks like. Give me an example.
Yeah. Oh, okay. So.
Yes, it is not causal. At the time t is equal to 1, it depends on input at -1, so it's past. That's okay. But at time -1, I depends on the input at 1, which is future. So it is not causal. So being with memory doesn't necessarily mean that you are causal, although we can come with zillions of examples with memory which is causal. And we are left with only memoryless. A system which is memoryless means that now I only depend on now, which means definitely causal. So if we are memoryless, definitely we are causal. If we are causal, we don't know if we are memoryless or with memory. So it's one-way direction. The next property is called stability. And stability is a very famous property. It's called BIBO. Do you know what is BIBO? Bounded input result into the bounded output. Now, is this signal? It starts. Let's do it in discrete. So minus infinity to plus infinity. Is it a bounded signal? Martin, is it a bounded signal?
I think yes.
Anyone objecting with that? Abdulaziz, is it a bounded signal? We start from minus infinity and we go to plus infinity. Is it a bounded signal? What is the definition of a bounded signal? Let's put it in that form.
A specific region.
Sorry?
It's within a specific region.
It's a very political answer that you gave me. It's in a very specific region. This is correct, but if you tell me what do you mean by region?
We have some boundaries that are not infinity.
Okay, let me put the question in this form. When we have a signal, we are talking about two variables, two parameters. One is time, the other one is the magnitude. So when we say that the signal is bounded, what should be bounded? The time or the magnitude? Magnitude. Because time is always from minus infinity to plus infinity. Maybe you are 0, but it's always from minus infinity to plus infinity. So when we say that the signal is bounded like this, it means that you can draw a line and you can say that the absolute of xn is less than a coefficient, a constant b. This b means maybe is 1 billion, but it's a constant. It's not infinity. So Abdulaziz is right. You are Martin is right. But you have to define what you mean. Is it in the magnitude or is it in time? And in the BIDO, which means that bounded input and bounded output, we mean that in the magnitude. In other words, if the magnitude is limited and I give it to our system, I will get an output which is again in the magnitude, it is limited, it's bounded. If the system is not stable, it means that I give a pulse and I get result of infinity. For instance, for this one, for this input, which is very bounded, we understand this, assume I have a system like this. Yn is equal to 1 over n xn. Is it stable? Suman, is it stable?
Yeah.
Why?
It has a bounded, I guess.
Sorry?
It has bounded, I guess.
I give a bounded input and I get a bounded output.
Can go if you know.
Okay.
No, Suman will tell me.
Yeah, 0 it goes.
Yes. Although I give a bounded input, because at time 0 I will shoot out. So it means that this is not stable. Actually, when you have a denominator, it's very easy to check. Just check whether your denominator will become 0 at some point. If it is, then it is not stable, right? And if I have this, definitely it will be stable. If I have yn is equal to e to power xn, definitely it is stable, right? So we have seen bounded input, bounded output, and by bound I mean that look at the magnitude. Now, I erase these ones because I want to talk about two very important properties, which are basically linearity and time invariant. Let's see what we mean by time invariant and what we mean by linear. So let's start by talking about this time invariant system. So we talk about 6 first and then time invariant system. So what is the trivial definition of time invariant system? Which type of system is called time invariant? If the output does not vary based on the time, in other words, it depends on the input at that location. If I'm shifting the input, the output will be shifted the same way. In other words, if I hit the board, it makes this sound. If I come next week and I hit the board in the same situation, I get the same sound. So it means that this is a time invariant. We know most of the systems that we have actually are time invariant because you hear this one, and we know that after I hit it, this, I don't know, mulkul will start to shake, and they can cause some increase in the temperatures, or the distance will be changed, and then I hit it at the same point, and the next time it will not be exactly the same thing. So we have a little bit of change, but it will come back to this reasonable mathematical model. It will become to unmodeled part of the system, which we ignore them, right? So although everything is time invariant, we try to keep it as time invariant as it is possible in our definitions because it's easier. So a system is either time varying or time invariant. Not both. This means that it is a binary property, like a switch, the switch is binary property. Either it is off or it is on. It cannot be on and off at the same time, or it cannot be none of them. Right? So time invariant is a binary property that we have. A time, I use Ti, which means a time invariant. A Ti, time invariant system does not change its fundamental behavior over different period of time. Its parameter values are constant. Like in Newton laws, F is equal to ma. We say that m is constant. Reality, m is changing. You send a rocket to go up, the fuel is being consumed, so the map of the rocket is changing. So it means that the m is changing. However, I said, for the simplicity, we keep it the same. A time invariant system satisfies the property that if xt give us yt, then xt minus tau will give us yt minus tau. So the same shift, the same time shift will affect on the output. In other words, we can say that we have the system and we have a delay. And we call it y, if this is y1t, we call it y1t minus tau. And now we have a delay, which means we have x1t minus tau. We give it to the system and we get y2t. So this is our x2t, right? So if y2t is equal to y1 t minus tau, then the system is time invariant system. So this is how a model represents. But let's see how we can test it. There are 3 steps analysis. Step 1, in your model, by model I mean the mathematical model, yn is equal to xn, like something like that. In your model, change all t's to t minus tau. Okay? So wherever you see t, put t minus tau. Step 2. In your model, change xt to xt minus tau. So this time I don't care about t. Wherever I have xt, I take xt and I put xt minus tau. And step 3 is if what I get in 1 is the same as what I get in 2, then it means the system is time invariant. Otherwise, it is time variant. Very famous example will be this. Yn is equal to xn squared. You want to see if it is time invariant or not. Step 1 was, let's call it yn is x, in a set of t, I put t minus tau, so I put n minus, let's say n0, whatever you like to, a square. Step number 2, I call it y2n, in a set of xt, I put xt minus tau. So instead of xn, I put xn minus n0. So this is my xn in the model, so I put xn minus n0. And step number 3, as you can see, y1n is equal to y2n. So easily we get that this is a time invariant system. Whereas in the next example, what we have is yt, let's do a continuous one, t xt. Okay? Step 1, y1t, instead of all the t's, I put t minus tau. Step number 2, instead of xt, I put xt minus tau. Right? So it will be t xt minus tau. So step number 3, are they the same? No. So we get that the yt is not the same as y2t. So we get that we have time varying system. We have a time varying system. The next property was linearity. We talked about linearity and then we finished today's lecture. What is a linear system? A system is linear if it has two properties. What are those two properties?
If you change the input and output,
If you what?
if you increase the input and the output increases proportionally, linearly.
What is that linear? What are the two properties?
Acceleration.
Hmm?
Acceleration will be the same.
Well, no, the two properties, one of them is the scalability. If you scale your input by alpha, your output will be scaled by alpha. Because the word that you said is very critical. I can increase my input by 5 and the output by 10, then this is not linear, right? But both of them have been increased. So they have to be, if I scale my input by alpha, I have to get the same scale of increase for output. And the second one is additivity. If I add input 1 by input 2, and I give it to the system, I have to get the output of the first one alone, plus the output of the second one alone. This is something that you have in our secret theory called superposition. You remember? So let's see how we can understand the system is linear. And system is linear if we have the x1t gives us y1t, and x2t, I mean I write in the continuous form, but you understand that this is valid also for the discrete form. y2t, then alpha x1t plus beta x2t will result into alpha y1t plus beta y2t. Right? Very clear form is if the input, if the output is like power 2 or power n, and n is not one of the input, then it is not linear. Right? Then we have the parabolas, or we have the square roots. As an example, we can talk about this system. System yt is equal to xt squared. Is this one linear or not? I just give you an example that is not linear. And we say that assume x1t, sorry, y1t is x1 squared t, and y2t is x2 squared t. Now, yt is alpha x1t plus beta x2t squared, which is alpha squared x1 squared t plus 2 alpha beta x1t x2t plus beta squared x2 squared t, which is not, it's supposed to be alpha y1, which is x1 squared t, plus beta y2, which is beta x2 squared t. So we can, as a conclusion, we get that this is not linear. Okay? So this is not linear. And we can have hundred thousands other examples which are linear. Most of the differential equations that we will solve are linear, and we will start to do some examples by talking about these linear differential equations. One thing is, in this course, we will focus on LTI systems. So the systems which are time invariant and the systems which are linear. Then it means that we can easily handle and use so many properties that we have in the differential equation. Do you have any question? If you have no question, you can stop.